Welcome, class, to our next lesson in automatic transmissions, transaxles. And we'll talk about hydraulic control valves and solenoids. So we got into, in our last lesson, hydraulic systems and different components of that. We'll talk a little more about the different control valves, how this works, and then also electrical solenoids that in our modern elect transmissions, how they work and how they control fluid flow. So our objectives, we're going to talk about the different valves that we find in automatic transmission transaxles. We're going to talk about accumulators and orifices, the different components in an automatic transmission that help control fluid flow in the automatic transmission. We'll talk about solenoids, the different solenoids that are in the automatic transmission, how they operate, including pressure control solenoids. So until the late 80s, into the 90s, when we started seeing electronic transmissions, all transmissions were hydraulically controlled. No computerized systems were part of it, and those hydraulic controls is what determined when and how a transmission shifted. And a transmission needs to know two things, even if it's electronically controlled. They need to know how fast the vehicle is going, so they need to be able to determine vehicle speed, and they need to know the load that the engine is under. And when we're talking hydraulically controlled transmissions, we used a governor to detect vehicle speed and a throttle cable and valve or a vacuum modulator to determine the engine load. And we'll discuss what these different systems look like and how they worked. Again, we're going to focus on the hydraulic controlled systems first, and then we'll move into electronic systems later. So when discussing a governor, the governor is connected to the output shaft of the transmission. So whether we're front wheel drive or rear wheel drive, the governor is connected to where the rear wheels or where the drive wheels are connected. So if we're front wheel drive, it's to the front wheels. If it's rear wheel drive, it's to the rear wheels. But anytime the wheels are turning, it's going to turn the governor. Okay, so how the governor works is as vehicle speed increases, centrifugal force pushes a pair of weights back against some springs, and it also moves a valve when it does this. Okay, when it does this, this allows fluid pressure to move past that valve inside the governor, and then it uses that fluid pressure to act on shift valves, and that determines when a transmission shifts. What happens is how governor pressure is related to throttle pressure is one has got to overcome the other one to create a shift. When you're accelerating, governor pressure has to overcome throttle pressure to determine when it shifts. So the heavier you're pushing down on the throttle, the faster you got to go to create more governor pressure to overcome that throttle pressure, and then the vehicle will shift. If you're cruising at highway speeds and you want to pass somebody and you step down on the throttle real hard, then throttle pressure overcomes governor pressure, causes the transmission to downshift, and then you can pass somebody on the highway. But governor pressure and throttle pressure act together. One has got to overcome the other one to control shifts inside a transmission. Here's a picture of a governor. This is a typical governor that GM used for a long time. If you look on the right side, that's a gear. There is a gear on the output shaft that meshes with this gear on the governor, and that turns the governor. That whole governor assembly moves. And there's a valve inside that governor. And there on the left, those arms, or whatever you might want to call them, weights on the outside, actually, as you spins, will flex outward. There's tangs on the inside of that then push down on a valve and allow fluid pressure to move. When they're at slow speeds, they don't have as much force pushing that out. When at higher speeds, there's a lot more force, centrifugal force, holding those weights out. So that's why governor pressure increases as speed increases. Here is a governor. This is off a Ford transmission where it's not, we don't have two gears meshing together. This is actually slips onto the output shaft of the transmission. There's a pin or a keyway that keeps it locked into place so it doesn't spin on the output shaft, and then a snap ring holds it from sliding off the output shaft. So that whole assembly spins. So instead of weights, just centrifugal force wants that valve to move in the housing. The actual governor is that section on the left, where the section on the right is just the block that it bolts to that hooks onto the output shaft. So as the output shaft spins, centrifugal force wants to keep the valve inside that housing, wants it to push outward against spring pressure. Okay. Here's a picture. This is a throttle body fuel injection. We see our throttle linkage coming from the accelerator pedal. There's the cruise control cable. But there at the bottom is the throttle valve cable. And when we get into service and diagnostics, we'll talk about how to adjust those throttle valve cables if it has one. Okay. But, so when we step on the throttle, that pulls the throttle plates open, that pulls on our throttle valve cable, which moves the valve in our transmission, which increases throttle valve pressure, which means the governor has to go at a higher speed before it will shift, overcome the throttle valve pressure, and then it will shift the transmission. Here's a vacuum diagram of how a vacuum modulator works. As you lose vacuum, our valve moves and adds fluid pressure to a boot pressure regulator valve and boosts the mainline pressure. Okay. What it does is it increases tension on that spring. So it essentially makes that spring stronger spring. So the pressure acting against that spring, if you remember from our last lesson, it's got to overcome that spring pressure. It'll take more mainline pressure to overcome that spring and thus increase our overall mainline pressure. Now we'll talk a little bit about our shift valves. We've talked about them some in the previous lesson, We talked about, when we're talking about governor and throttle valve pressure, how these work. Our shift valves is what actually gives our shifts in our transmission, our different speeds in our transmission. So a valve has to move one way or another to get the transmission to shift. And then you do that by pressure. Pressure increase on one side moves and it decreases on the other side. The valve moves, and vice versa. And these are used within with springs to determine when that valve moves. Okay, when you're at rest or at slow speeds, that spring pressure moves the valve to its rest position. Okay, and then when you speed up, the governor pressure acts on one side of the valve, while throttle pressure or load pressure from the modulator, whichever one you're dealing with, but either way, that's the load of the engine, is acting on the other side of the valve. So governor pressure has to increase, so speed has to get up to a certain point to overcome or be able to push that valve against the throttle pressure. Okay, the harder you're accelerating, the more governor pressure it takes to overcome that throttle pressure. That's why when you're accelerating harder, shifts are later. When you're accelerating lightly, shifts are earlier. They do that again because under heavier loads, we need to make sure that we have more pressure applying those clutch packs. Here's a hydraulic diagram of what's going on when it shifts. If you look at the upper one, this is our 1-2 shift valve, and we have throttle pressure on one end, governor pressure on the other end. It gets up to a certain I should say speed, depending on how much throttle pressure we have. Again, if we're gradually accelerating, that governor pressure is going to be able to push that 1-2 shift valve easier than if we're accelerating hard. But either way, what happens is, as you can see in that 1-2 shift valve on the upper one, it's at rest. The 1-2 throttle valve is pushing against the 1-2 shift valve. The spring is pushing on that 1-2 throttle valve. TV stands for throttle valve. Then once a certain speed is reached, there's enough governor pressure created, as you can see on the bottom picture, that it pushes the 1-2 shift valve and it overcomes that throttle pressure. It closes the port off for the throttle pressure and opens the port for your second clutch to apply second gear. When we get into diagnostics of a transmission, we will talk about fluid diagrams. I will try to load them the best I can. They are very elaborate. It's hard to get a good picture of them on a PowerPoint, but I will at least try and put them up there or tell you where you can go in our service information to find them, so you can see what a hydraulic diagram looks like for a transmission. They look a lot like a wiring diagram. They use different colors to give different hydraulic systems, and they show all the shift valves in the valve body in the transmission. Okay, when we're talking about shift quality, we have what we call shift modifiers, and they use valves, or as we'll talk here in a minute, accumulators, to help adjust the speed and firmness of a shift. Okay, in early transmissions, we're talking 60s and 70s, even a little into the 80s. These transmissions were really simple, didn't have a lot of shift modifiers. But as we started adding more gears, people expected more comfort out of their vehicles, that they wanted the transmission to shift a lot smoother. They didn't really want to feel those shifts. So they had to start adding valves and accumulators to start compensating for that. But we had to make sure that we still had plenty of fluid pressure to apply and hold that clutch tight so we didn't burn the transmission up. So these shift modifiers come in play in several different places. First, our light throttle shift. This is made when the engine's not producing much torque and can be pretty slow and at light pressure. So when we're barely accelerating, we get a shift. The transmission can shift, and it'll be a nice smooth shift that people won't feel. Under heavy throttle, the engine is producing much more torque. So we need a shift, like I said, that will hold those bands tight. So we're going to get more pressure, so the shift's going to be firmer. We need a way of controlling those. Even under heavy throttle, most people do not want a real hard shifting transmission. A hard shifting transmission is actually a better shift, at least for the transmission, as long as it's not too hard. Because that means the clutches are slipping less and applying tighter sooner. So we need to have valves and stuff in place to help those shifts. Okay. Too slow of a shift means the speed of a shift is from when it starts to shift, when it first applies pressure, and when the clutch pack completely engages. Okay, think of it if you've driven a manual transmission, from when you start letting out on the clutch until you've lit that clutch all the way up. That time is the shift. The slower you let that clutch pedal up on a manual transmission, the more that clutch shifts. Yeah, you accelerate smoother. No, it's not so much bucking or a hard engagement, but it does slip that clutch. Same concept in clutch packs and automatic transmissions. They engage them a little slower for a smoother shift. But if it's too slow, it slips too much and it can burn that clutch pack up. Okay? Too fast of a shift, and customers are going to start feeling that. Because a fast shift is almost always felt in a firmness. So if it's too fast, customers will feel it and they will complain about it. So that is the balance that you have to get that the manufacturers try to find when building these, and that when we're rebuilding those, we try and find a way to firm the shifts up, repair any defects caused from wear on the original design, and we try to find a way to maybe firm up the shifts, shorten the shifts, without making them too harsh to where the customer complains. Another way they use to control shift quality and these shift modifiers is through what we call accumulators. These accumulators are tied hydraulically to a clutch or band servo. In other words, they help control the hydraulic pressure applied to a clutch pack or a band. It absorbs the fluid during the pressure buildup stage. As fluid is filling the cavity to apply that band or servo, that's our pressure buildup. That's our length of shift. It absorbs some of that fluid pressure, you might say, to help smooth out that engagement in that clutch or band. And that lengthens the time so it's not too short and too harsh. How it works is, as clutch or band apply pressure is entering the apply side of the accumulator, fluid must leave the opposite or exhaust side of the accumulator. All right? How much fluid pressure in there is on the exhaust side will help determine, or how fast that fluid pressure exhausts determines how much of that fluid pressure it absorbs and how that transmission shifts, how that clutch pack or band applies. Let's go to the next slide. So here's an example of this. On the top part, the red, that is the fluid coming from the shift valve that is actually going to apply the clutch. Okay? Your piston in your accumulator separates the two sides. Your apply side and then the accumulator side. The pink is your accumulator side. So they use, in almost all your accumulators, they use a spring to help cushion that. So when pressure comes in to apply that clutch, it pushes down on that piston. That helps increase the time that it takes to apply that clutch. The idea is that it applies that band or clutch slower and smoother so you don't get such a harsh shift. That spring and the fluid on the back side of that helps control that. If we had more pressure on the accumulator side or the exhaust side, it would mean a harsher shift. If we had less pressure, that means a longer shift. You can get what we call a slide bump shift. Say that spring is broke or we have improper accumulator pressure to where they can push that piston down too fast. It'll have a long shift because it pushes that piston down and has more room, space it has to fill up, but it pushes it down really fast. So we'll push it down fast and then it will hit solid. So that slide bump is usually from incorrect accumulator pressure or a broken spring in the accumulator. Okay, and that'll almost always lead to a customer complaint. This happens a lot in transmissions with age where the accumulator gets spring gets broke or wear in the transmission causes pressures not to be where they were designed to be, and you get these improper shifts. But the whole idea of an accumulator is to soften and lengthen that shift in a clutch pack. You can modify these. In most shift kits, they do modify them. We change through controlling the size of orifice that applies that pressure on the accumulator. We change springs in these to change that accumulation rate or that accumulator rate to change how that clutch pack or band applies. Here's kind of a diagram to show how this buildup happens in a pressure system. If you look at diagram A, you'll see is that the line starts to gradually rise. This is the pressure rise to fill the clutch circuit. That's all the passages, accumulator if it has one, into the actual housing that holds the clutch pack or the servo that applies the band. Okay. The next line is the actual stroke of the clutch piston or the stroke of the servo that's applying the band. And then as you see, that next line goes straight up in a system that does not have an accumulator, or maybe there's a default in that accumulator. That pressure rises rapidly. And when it gets to full application, as you can see anything, if something rises rapidly, then stops rapidly, there's a harshness to that stop. And that's what happens in a clutch pack or a band that doesn't have an accumulator. Once that pressure rises rapidly, then stops, then you get a harshness to your shift. Where B, you can see with an accumulator, that rise of pressure happens gradually and more of an angle before it finally fully fills up. So there's less harshness to that shift. The shift takes longer, but there's less harshness to it. That's why designers of transmissions, there's a lot of engineering going into this. We want comfort for the driver so they don't complain, but we don't want it so soft or too long of a shift that it burns up the transmission because of heat and slippage to wear the transmission out prematurely. Another way we control the flow of fluid is through check balls. These are simple devices. They are actually little balls that are used to help control fluid flow. Usually made of steel, but they can be nylon, rubber, or some other composite material. But steel are the most popular. Sometimes if you get a valve body shift kit, sometimes they'll replace a steel with a bigger nylon one to fit a hole that maybe is worn out. Okay. These check balls can be one-way or two-way check valves or check balls. Can be located in the valve body or the case side of the transmission. Somewhere in those passages, you'll see a valve body, and many times what they're blocking or opening up are holes in the separator plate. If you remember, that separator plate goes between the valve body and the case. Here is a one-way check valve. What usually happens with a one-way check valve is it is designed where you'll have two holes in your separator plate. You'll have a big hole and a little hole. They use that check valve to help control how much pressure goes to a clutch pack. When you go to apply pressure, let's say the one on the right, where it says no flow, a good way of thinking that of those arrows is when they're going to apply pressure to the clutch pack. So it goes down and it pushes that check ball down into the larger hole. Well, there's a smaller hole next to it that the fluid is able to go through, and that smaller hole, when we start talking about orifices here in a minute, it actually reduces the pressure, so it applies the clutch pack softer. Then when they're done with that clutch pack and they release that pressure, they want to get the fluid pressure to exhaust out of there faster. So that would be the left side. That's actually exhaust. So the pressure runs out of that clutch pack. Well, they want to get it out of that clutch pack as fast as possible. So it'll push that check ball off because it's coming from the other direction. And it'll go through that bigger hole and exhaust the fluid quickly. In modifications, sometimes several things will happen. Sometimes in some shift kits, especially in performance shift kits, you might just take that check ball out altogether. So it'll apply through both holes. So it'll apply that clutch pack very quickly with a lot of pressure and hold that clutch pack very tight. And then it'll exhaust really quickly also. Or you can take and drill that smaller hole out a little bigger. So the fluid that's coming through the small hole is more than what it was originally. But that's essentially what a one-way check valve is like. You usually see them in a spacer plate where you have a big hole and a little hole. And that check ball is to block that big hole. They block the big hole when they apply, and then when they exhaust the clutch pack, it pushes the check ball away so the fluid can come out of the clutch pack fast with low restriction. In a two-way check valve or check valve situation, depending on which way the fluid flows. Say their passage is coming from B, as you can see, it'll push fluid up, it'll move the check ball into the one hole, so fluid doesn't backfeed back down A, because that may be connected to some other check circuit that we wouldn't want fluid flowing in at that point. And then when they decide to quit the fluid flow on B and apply it on A, then the check ball is able to move over and block the passage in B. This is usually you find on the separator plate, two usually same size holes right next to each other. And if there's a check valve in those, that means it's meant to move back and forth depending on where they want to block and where they want to apply. When we're putting shift kits in, or if we're moving check balls, this is a check ball you almost never take out unless you make major changes to the separator plate or the valve body. Because if you would take one of these out or forget one of these, then it would apply pressure into a circuit when the transmission is not wanting pressure there. And that's almost always going to cause shift problems and or major malfunction in the transmission. So we know on our check valves, those are meant to help control fluid flow, blocking holes and opening holes depending on the flow of the fluid. And that brings us to our orifices, these holes that are in our separator plate that act as restriction to fluid flow. When we restrict fluid flow, we get a pressure drop as long as fluid is flowing through it. If there's not fluid flowing through that circuit, say there's just residual pressure in that circuit, or once that pressure equalizes, and we'll see that in a picture here coming up, then the pressure is the same. But as it flows through that orifice, there will be an initial pressure drop. Okay? That is how we can help control fluid flow. That's used commonly when we're applying clutches. That's that big hole and small hole. We use that smaller hole so we apply the clutch slower and softer. That's for comfort reasons. There's some cases, like I said, in shift kits, you can take a check ball out. It'll apply through both those holes. It'll apply the clutch pack faster and harder. But in some cases, even for hot rodding use on the street, that just makes the shift really, really hard and really uncomfortable. So a lot of times in those cases, we'll just drill that small hole out a little bigger. But those orifices are small holes in the separator plate that actually control how much fluid pressure is applying. Here's an example of this. This is an orifice that is controlling fluid pressure to a clutch pack. So they're applying 60 pounds, but when it hits that orifice, it's a restriction. So think of it as our voltage and amperage. Our voltage is our pressure, but our ohms of resistance is our restriction, and it drops our amperage. Okay, that's the actual fluid flow through the circuit. So as soon as it hits that resistance, it drops our pressure. So less pressure acting on that clutch piston means less force. So the clutch pack applies smoother. But once that clutch pack fully applies, as that fills that capacity all the way up, it essentially stops the flow of fluid because fluid has filled that up. Then the pressure equalizes and you get a full 80 pounds to hold it. So it takes it uses less pressure to apply it, so it applies smoother and slower, but it has the full 80 pounds to keep it held tight. Okay, now we're going to talk about the hydraulic subcircuits. And when I'm talking subcircuits, we're talking about the different actual hydraulic circuits within a transmission. First, we have supply, and supply is basically the fluid pressure or fluid in the pan that the pump picks up. So the pump picks the fluid up through the filter in the pan or the sump, and it puts it into the pump, and this is our supply circuit. Once the pump pressurizes that and pushes it through the transmission, we have a regulator there to control the exact pressure. That's our main line pressure or our main control pressure. Then we have a converter cooler pressure circuit. That is the circuit where it goes out in our lines through our cooler. First it goes to the converter, then our lines to our cooler, back to our transmission where it lubricates our bushings and our planetary gear sets, and then back to the pan. Then we have our drive circuit, and this is what applies our forward clutches, our forward clutch, and it supplies all our circuits for our forward gears. This is a lower pressure than our reverse pressure. Our reverse pressure, and this could be our low reverse pressure too, because in manual low gear, it increases pressure also. So manual low would be the same circuit as our reverse circuit. That, when it goes into that circuit, it increases mainline pressure. Okay, so when we have our reverse circuit, that increases our mainline pressure and allows us to apply manual low gear and reverse with a higher pressure to hold the clutches tighter. Then we have our governor circuit, and this is our pressure that after it's gone through the governor. Depending on this vehicle speed, the dependent will dictate how much governor pressure we have. Then our throttle valve or our modulator pressure, this is, as we've talked about, is our pressure that's controlled, that tells us the load of the engine. This is a whole other different circuit from our other circuits. And then our accumulator circuit. As we talked about our accumulators, this is what is on the back side or our accumulator side of an accumulator to help control how a clutch pack or a band applies. Now that we've talked about our hydraulic circuits, we'll start talking a little bit about transmission solenoids. Remember, we've had electronic transmissions since the late 80s, and by the late 90s, definitely by the late 90s, about every transmission out there was electronically controlled. And we're going to talk about the solenoids in those circuits, okay? These are electromagnetic switches. If you remember the difference between a solenoid and a relay had a movable arm, where a solenoid had a removable core. They were both electromagnetic switches, but the solenoid have a movable core. That core is what moves to control the fluid flow. Okay. Two basic types of solenoids are on-off and pulse width modulated. Almost all our shift solenoids are on-off, where our pulse width modulated solenoids are, many of those are our pressure control or our torque converter solenoids. All these solenoids are controlled by the PCM or TCM. Remember from our acronyms, PCM is powertrain control module, TCM is transmission control module. Some vehicles use a separate module for the transmission. Many vehicles incorporate that into the powertrain control module. Here's a quick breakdown of a solenoid. As you'll see, we have a basic housing that holds the components. We have a spring that is meant to keep the metering vault, that movable core, and they're going to call it different, a plunger, a ball, a pintle. Remember, this is going to work almost exactly like, say, a injector. So you have a spring holding that movable core in the rest position, whether it's normally open or normally closed. We have a coil assembly that we apply power and a ground to that energizes the coil, creates a magnetic field, and moves that movable core. Okay? In this case, we're going to have fluid that then moves into the solenoid. Depending whether it's normally open, normally closed, and we'll talk about, will dictate exactly how that solenoid controls fluid pressure. But the basic concept of all of our solenoids is we're using an electric coil assembly to create a magnetic field to move a plunger to control fluid pressure. Okay, now that we've talked about how these solenoids work, the construction of them, we'll talk about the two different types. On-off solenoids do exactly that. We turn the solenoid on and off, the computer does. These solenoids are usually got power applied to them, usually battery voltage applied to them, and then the computer controls the ground side or the low side of the circuit. When they want to energize the solenoid, the computer applies a ground path, current's able to flow, energizes the coils, creates a magnetic field. When they de-energize it, they're releasing the ground path, and there's no path for that current. No current flow means no magnetic field. They can be normally open or normally closed. A normally open allows, a normally open valve allows fluid to flow when it's not energized, but as soon as you energize it, it blocks the fluid off. Normally closed valve blocks fluid flow when it's not energized, but as soon as the ground path is applied, it moves the plunger and fluid is able to flow through the solenoid to the valve. On-off solenoids have two states depending on the application, depending on the manufacturer. an apply state or a venting state. An apply state, means that fluid is applied to the shift valve when it's energized or de-energized. In other words, there's no fluid there, then they apply fluid to move the shift valve. In a venting one, there's fluid there, and then to move the shift valve, they vent the fluid. Okay? And then once that fluid's vented, the pressure's vented, then the shift valve moves. It'll be either or. The main idea is they're controlling fluid pressure to get a shift valve to move. Here's an example of a on-off solenoid being operated. You'll see in the off position, this is one where it's normally open. You see how the fluid is able to flow through the valve. But as soon as they energize it, goes on, the plunger moves, blocks the fluid flow, and it's not able to flow through the solenoid. That's a simple operation of an on-off valve. Before I go into this pulse width modulated solenoids, and we'll get into this a little more when we talk about electronics and diagnosing them on transmissions, but how to think of solenoids in a transmission in a hydraulically controlled system. We have a governor and a throttle pressure, and they've got to work against each other to get the transmission to move. In electronically transmission, they still monitor the load of the vehicle and speed of the load, but no longer are those directly affecting the shift valve. All they're doing is telling the computer that they need to operate fluid pressure in conjunction with the load. So if you remember our computer systems, we have inputs and outputs. If you remember when we were talking about electrical, how we changed things, it used to be before computer controls, if we had a switch, all the current would be going through the switch. Now with computer controls, our switches just tell computers to control the device. That's what's happening on electronic shift transmissions. Instead of having the hydraulics of the throttle valve and the governor directly operating the valve, now we can monitor vehicle speed, we can monitor engine load, and adjust shift solenoids and pressure solenoids to control pressures in the transmission to get it to shift at certain speeds and RPM. So now that we've talked about on-off solenoids, we'll talk about pulse width modulated solenoids, and we talked about pulse width modulation. They use a set frequency, but they just, or set voltage, but how much voltage is applied or how long the voltage is applied changes. It has the same voltage, but they change how long that's applied to the solenoid. That's our duty cycle. We see it in, or pulse width. We see it in injectors. We see it in our fuel pumps on some of our fuel systems to control that solenoid on a pulse width modulated solenoid. How long they keep it energized is our duty cycle. So they can change the duty cycle to gradually apply something or gradually control the pressure. It's just not on and off. A real typical application for this is torque converter clutch apply circuits. The early days of torque converter clutch applies, they were on-off solenoids. But to increase the comfort of that shift, so customers actually didn't feel that torque converter apply, they would use pulse width. So they could change the duty cycle to change exactly how much fluid flow is going through to control how much fluid flows through. So completely de-energized, it's 0%. 100%, fully energized, it's 100% duty cycle. And then it'll range somewhere in between there, depending on the load, depending on the speed, will depend on how much fluid pressure or fluid flow they want going through that solenoid. A type of pulse width solenoid is a linear solenoid. It actually has a valve in the solenoid, a spool valve. It's not a plunger with a ball on the end of it like you've seen in a lot of our on-off solenoids. Many, if not most, of your pulse width solenoids are linear, and they're going to use a spring and a spool valve in the snout of the solenoid. Here an example of a linear. They call it linear because it's all in line with each other. As you see, the spring is on the end of the valve, and then the plunger is pushing against the valve. So instead of a ball that's just closing one single port off, it moves that plunger, which moves the valve a certain distance. It's not wide open or completely closed. We can control the range of that valve, and that's what most of our pulse width modulated valves, or many of our pulse width modulated valves are linear valves. Our other type is our pressure control solenoid. Okay, this is what directly controls our mainline pressure. No longer are we using a pressure regulator valve. Well, I'll take that back. We're using a pressure regulator valve, but we're using this solenoid to control it. If we want more pressure, we put more pressure against the valve or exhaust less pressure. Remember, whether it's an apply or venting valve, solenoid, pressure control valves, pressure control solenoids can operate the same way, but they can control, essentially, they take place of the spring portion of the regulator. Okay, they control how much pressure it takes to overcome that valve, which gives us our mainline pressure. Some common names: electronic pressure control, EPC, or just pressure control, PC, variable force solenoid, VFS. Another common name you'll hear is force motor. It's just a little solenoid that controls the actual pressure in the transmission. In most transmissions, we can get in there with a scanner and control that solenoid to control our fluid pressure. That one transmission that we had, one truck that we had in the shop that we did some work to, we put the differential in it. And then it didn't want to shift. One of the checks we did, we hooked a pressure gauge up to it, hooked the scanner up. We could control the pressure control solenoid to see if it controlled our pressure. And when we get into diagnostics, we'll talk a little bit more about how to monitor and how to diagnose issues that might be related to our pressure control solenoid. Here's an example of a pressure control solenoid. Here's our pressure regulator valve. It does have a spring. Some do, some don't. But that spring is just mainly to put the valve back at the rest position. There's not that much pressure. It takes very little pressure to overcome that valve. The EPC solenoid, the pressure control solenoid, is what actually controls how much pressure is on the one valve. If you see at the bottom of the picture, it puts pressure on the back of that valve. So it takes more line pressure on the very top to move that valve and exhaust pressure. So if they want more pressure in more mainline pressure, they apply more pressure to the backside of that valve. Some, this is an applied type. Some, there's pressure on the back of that valve, and then they'll use a solenoid to exhaust pressure in order to control how much pressure it takes to push that valve, and whether it increases or decreases mainline pressure. Here in this, they have a transmission control module controlling it. Many vehicles, they use the powertrain control module to control this solenoid. And what they do on most of these, on many of these, they'll have power to it and they control the ground side of it. Here is just kind of a breakdown of a valve body in a transmission. You'll see the different valves and springs in the valve body. You see solenoids hooked in there also. This is a pretty common look of what you'll see in a valve body on an electronic shifted transmission. Okay, so now that we've went through our different control valves and solenoids and kind of how the hydraulic pressure works in a transmission. Again, this is why we call valve bodies the brain. The pump is our heart of a transmission, but it's all centered around hydraulic pressure, hydraulic fluid flow. We need this hydraulic fluid flow to be correct, properly applied, properly regulated, to get our shift points where they're supposed to be, and to get our transmission to shift in a way that the customer is pleased for it to shift. Next, we're going to move to our torque converters. And once we're done with the torque converters, that'll complete our section on torque converters on hydraulic systems. After that, we'll move on into the internal parts of a transmission.